IRT and RQA. The explanation below is written in full sentences so that even readers new to IRT and RQA can follow along, describing what the code does, why it does it, and what each line means. It also interprets what each visualization shows, and concludes with common practical issues, tuning tips, and cautions for applying the workflow to real data. First, let's summarize the overall objective. This notebook builds a complete pipeline that constructs a person's time-varying ability theta, t, and uses RQA, Recurrence Quantification Analysis, to quantify when and to what extent repeating or laminar patterns appear in the theta, t, time series. To do this, we first simulate synthetic response data, respondents times items, and fit a 2PL-IRT model to estimate item parameters, discrimination A, difficulty B, and ability scores, theta. We then create a temporal session for a single participant and update theta, t, online. For the resulting theta, t, we compute embedding, select a radius, generate RP/DRP, and calculate RQA metrics, det, lam, entr, tt, then track how these metrics change over time via windowed RQA. Finally, we compare cross-recurrence with reaction time, RT, using CRQA and refine theta, t, via Kalman smoothing, KFAS, comparing the results from an RQA perspective. Starting with package preparation and environment setup, the code loads LTM, MIRT, ggplot2, dplyr, tidyr, per, krka, pragma, kfuzz, psych, scales, cowplot, grpl, and grplot, and suppresses startup messages with suppress package startup messages to keep output tidy. It fixes the random seed with set.seed42 for reproducibility. Since reshape2:melt is called when drawing a heat map for the distance matrix, you will need to run install.packages reshape2, once if reshape2 is not already installed. Missing this installation can cause errors, so take care. Now for step 1, simulating cross-sectional data. We set the number of examinees to n equals 300 \, and the number of items to j equals 20 \. Each item's discrimination, a_j \, is drawn from a uniform distribution on 0.6 to 1.8, and its difficulty, b_j \, from a normal distribution with mean 0 and standard deviation 1. Examinee abilities, \theta_i \, are also sampled from a standard normal distribution. The logistic function logit x equals 1/1 plus expects, is defined, and for each examinee item pair the correct response probability is computed as px sub I equals 1, equals \text logit, a_j \theta_i, b_j \. Using these probabilities, we draw Bernoulli samples to form a 0-1 response matrix X. This setup implements the core assumption of the 2PL-IRT model, that abilities and item parameters determine response probabilities, via simulation. Plotting item-wise proportions correct gives an intuitive view of which items are easy or hard, and a histogram of theta shows whether the ability distribution in the sample is appropriate, i.e., not overly skewed. The console will output cross-sectional data size, 300 × 20 to report the data shape. In step 2, we fit a 2PL model with LTM using LTM-df_z1, IRT. Param equals true, where z1 indicates a unidimensional latent ability, theta. The matrix from cof_mod_2PL, contains item-wise discrimination, DSCRMN, and difficulty, DFFCLT, estimated independently of the simulated true values. Factor.scores, method equals EAP, returns the EAP, expected a posteriori, estimates of theta for each examinee. To assess estimation quality, we plot the item parameter scatter, B versus A, to visualize the difficulty discrimination landscape, and plot true versus estimated theta against the identity line to check how close the estimates are to the truth. Higher discrimination indicates an item more sensitive to differences in ability, while higher difficulty B typically means a harder item and lower proportion correct. Step 3 constructs a single person's temporal session and performs online theta estimation. We assume a session length of t equals 150 and define the truth eta, t, as a standardized cumulative random walk with a slight positive drift, modeling gradual learning over time. At each time t, simulate responses theta_t, a, b, generates item responses using the item parameters, a, b \, estimated in step 2. In practice, calibrated item bank parameters are often used. Then posterior_update_theta performs a simplified Bayesian update. Internally, for each item it computes the current predicted probability, p \, given the current theta estimate and the logistic information, a squared p1 p \, and combines a discrimination weighted score, observed response minus predicted probability, to update the variance and mean. Intuitively, performing better than expected on a high discrimination item raises theta more strongly, and performing worse lowers it more. After iterating across items, the updated mean becomes the online estimate theta_st. We plot the time series of true and estimated theta to compare trends, and separately plot the estimation error, estimate minus truth, to check for systematic bias over certain intervals. From step 4 onward we follow the RQA pipeline. The core question is, in the theta, t, time series, how often and in what patterns do past states recur later? We begin with embedding. Embedding unfolds a 1D time series into an m\dimensional state space. Here we set the embedding dimension to m equals 3 \, and choose the delay \tau by referencing the first non-positive crossing in the ACF, defaulting to 3 if none is found. For time t, the state vector is x_t, x_t \tau, x_t2 \tau. We compute all pairwise Euclidean distances among these vectors to form a distance matrix, d \, and then decide on a radius to define recurrences. The code sets a target recurrence rate RR of 5% and uses binary search to choose a radius that achieves it. A caution here is that the RR calculation includes the main diagonal, i.e. equals j, 0 distance to itself, which can slightly inflate RR. Strictly speaking, it is preferable to match RR after excluding the diagonal. We then call RQA to compute RQA metrics, using the chosen \tau m and radius. Min_diag_line and min_vert_line set minimal line lengths to exclude very short, likely spurious lines caused by noise. The key metrics are det, determinism, laminarity, entr, entropy, and tt, trapping time. Higher det indicates stronger regular/repeating structure and greater predictability. Higher lam and tt indicate longer laminar, stagnant, phases. Higher entr indicates a more diverse distribution of diagonal line lengths, i.e., more complex patterns. As a supporting visualization, a 50x50 block of the distance matrix heat map is shown. Bright, small distance clusters suggest groups of similar states. We then compute DRP, diagonal recurrence profile. DRP summarizes how often recurrences occur at specific lags. If drop fails or is unavailable, the code includes a manual fallback that constructs the binary RP and averages along offset diagonals. Peaks at non-zero lags indicate periodic recurrence with that lag. Next, we visualize the RP itself by marking points where d_la or long off-diagonal lines indicate repeated trajectories, determinism, while vertical/horizontal lines indicate laminar behavior, stagnation, complementing the interpretation of det/lam/tt. If the radius is too small and no recurrence points appear, the code defensively increases the radius to target RR by +2 percentage points and redraws. Step 5 is windowed RQA. A single, static RQA may miss when patterns change. We therefore slide a window of length 80 in steps of 10, retargeting RR equals 5% and recomputing RQA in each window. Faceted plots of det/lam/entr/tt/rr over time reveal intervals of increased regularity, high det, stagnation, high lam and tt, and changes in complexity, entr. The RP, off-diagonal, plot is overlaid with dotted lines indicating window centers, so that specific intervals can be visually aligned with RP textures. Going further, the code uses pragma: find peaks to detect peaks/troughs in each metric, draws vertical lines at those times, and adds value labels. It also provides an intermetric correlation matrix, grplot, and an entrtt scatter with a regression line, summarizing relationships among metrics. For example, lam-tt often correlates positively because more stagnation tends to lengthen trapping time. In step 6, we perform RQA, cross-recurrence quantification. We compare two time series from the same subject, standardized theta_st and a smoothed RTT obtained via a moving average. Passing them as TS1 and TS2 to RQA with the same embedding and radius settings lets us read RR/det/lam/entr as measures of structural synchronization between the two processes. For example, if theta increases while RT decreases, responses speed up. In a coupled manner, the cross-recurrence plot may show strength in diagonal texture and the metrics may be elevated. In practice, since the distributions and scales of the two variables differ, it is usually better to retune the radius for the pair or consider distance normalizations, for example, covariance normalized distances, to match sensitivity. Step 7 focuses on reducing measurement noise in the online estimated ability time series, producing a smoother and more interpretable trajectory, and comparing how this affects RQA metrics. Using the QFIS package, we build a state space model and apply Kalman smoothing. In code, the observed series is set from the online estimates, and its length is recorded. The observation noise variance is approximated from differences between the observed estimates and the simulated ground truth, a choice only valid in simulations. If this estimate is invalid, a default is used. The state noise variance is fixed to control how flexibly the smoothed series can evolve. Larger values allow more fluctuation, smaller values enforce smoother trends. A local-level state space model is specified, and Kalman smoothing yields a smoothed ability series. We extract that series and visualize it alongside the true and online estimates. If the smoothed curve fluctuates less while following the main trend more closely, smoothing has effectively improved the signal-to-noise ratio. Because the balance between state and observation noise controls the filter stiffness, practical tuning often relies on likelihood-based methods, information criteria, cross-validation, or domain-informed priors, estimating observation noise from truth assimilation only. Rerunning RQA on the smoothed series follows the same pipeline as before. We standardize the smoothed series, embed it with the same dimension and delay as the original, recompute distances, and retune the radius to hit the target recurrence rate, necessary because smoothing changes pairwise distances. We then compute RQA metrics. In practice, smoothing often increases determinism and laminarity/trapping time, cleaner, longer lines, while entropy may decrease due to reduced fine-grained irregularity. These outcomes depend on interactions among noise settings, embedding choices, and the targeted recurrence rate, so it is wise to compare multiple configurations. This completes step 7, concluding with an all visualizations completed message. Overall, the full pipeline, dynamic ability estimation via IRT, RQA to quantify recurrence and stasis, windowed RQA to localize temporal shifts, cross-recurrence with reaction time, and Kalman smoothing to stabilize metrics, supports quantitative assessment of individual dynamics in domains like education, cognition, HCI, and rehabilitation. Practical tips: tune the recurrence rate target within a reasonable range and avoid counting the main diagonal. Prefer mutual information for delay and false nearest neighbors for embedding dimension. Balance window size and step for stability versus resolution. Retune the RQA radius for each series pair. Choose Kalman noise parameters via likelihood, cross-validation, or domain knowledge. ensure required packages are installed and handle edge missing values when smoothing reaction times, and manage heavy computation with subsampling, dimensionality reduction, or parallel/C++ implementations. In summary, careful tuning and validation enable reliable detection of recurrent and stagnant patterns, change points, ability RT coupling, and more stable RQA metrics.